Welcome to a new problem solving session, and we are still doing problems of rotation of rigid bodies, and it's dynamics basically. And we are using simple things like instantaneous center of rotation. The force is the motion of its center of mass, and using equations of rotational motion, that is, you using a little bit of torque, and we are trying to solve these problems. This is one of the popular problem, and a statement of the problem is simply, as you can see at your screen, a weightless, inextensible thread is wound around a spool. Also, you don't need to worry about its shape because its moment of inertia is given. I know. As I'm going to follow the transcript of the problem, and you will see that everything else is given. A spool lying on a horizontal surface with the mass m, mass is also given, and moment of inertia is also given. So we do, and relative to its own axis. So we don't have to worry about. And the outer radius of the spool is 4 centimeter, capital R, that is, and inner radius small r is 1 centimeter. A force is applied to the end of the thread. Yeah, here the thread is wound, thread is wound over it, and a force is applied in such a manner. So you can see here, and what next? At an angle 60 degree to the horizontal surface, the force, and find the acceleration of the center of mass of the spool. That should be written as A, and the coefficient of friction for which such a motion is possible. And this is the problem, and we have to solve it, and of course we can do it. And now watch the picture along with it, this picture, and you can see here that we have selected a lab inertial frame, that means this x-axis, this x-axis, this y-axis, and this is z-axis. Of course, if this is x-axis, this is y-axis, then following the right hand rule, inside this xy plane should be the z-axis, and so it's done. X-axis, y-axis, z-axis, and I think the z-axis is drawn here because there is an instantaneous axis of rotation directed perpendicular to the parallel planes in which the body move, and of course, in the absence of any kind of slipping, the instantaneous axis of rotation passes through the point of contact of the spool, this is spool, and the horizontal axis beneath it. So I already defined the positive direction of the axis of rotation, that is instantaneous axis of rotation, and that is along the positive z axis, and yes, the positive direction of the z axis is selected as the instantaneous axis of rotation. And this is you can also see the origin of the coordinates is on one of the points of contact through which the instantaneous center of rotation passes. So nothing else, we need to define anything more. And as you can see here, we also have drawn a bit of its free body diagram, FBD in short, the force that was given in the problem, and we know a gravity will act, and a normal force here, and the force of friction here. And force of friction, direction of force of friction, you can easily recognize that it's creating some kind of rotation by creating an angular velocity in this direction. the direction of angular velocity is again along the z-axis. So this friction is responsible for that angular velocity, and these things are quite familiar to you. And let's write down the system of equations of motion of this spool or the wetless thread that is moving in our laboratory inertial reference frame. That means this frame is at rest, and with respect to the ground it is at rest. So it is inertial frame, lab frame. That means we have established our lab on this planet, and it is at rest with respect to the planet. So people in general refer it as lab inertial frame, inertial reference frame, you can say. And we are going to write down the equations of rotational motion around the instantaneous axis of rotation. This I love this in the instantaneous center of instantaneous axis of rotation. And so I'm going to write down the equation of rotational motion around the instantaneous axis of rotation, and of course the equation of motion of the center of mass of this spool in projections along x and y axis. I will cover x and y both axes because I need to find out the friction, the coefficient of friction at which such a motion is possible. So I'm going to use this y-axis projection as also. So what should be the equations? I thought it will be easy to write the equation of motion of the center of mass of this spool, and so I'm going to write it first along y-axis. And what is it along y-axis? I guess you can see something here like normal force acting upward, gravity in downward direction, and also a vertically upward force f, that is f sine alpha. So f sine alpha and n coincides, so we have n plus f sine alpha, and that should be equal to mg, and this is the first equation along the y-axis. And now I'm going to write the equation of its center of mass along, no, this equation was x-axis basically, sorry. I was even not looking at those axes, and I was just speaking. So I'm sorry. This is basically x-axis. Now I'm going to write the equations along the y-axis. And y-axis, I can see two forces are acting on this pull. One is F cos alpha towards right, and second one is the friction force towards the left. So I'm going to write this equation as F cos alpha minus F, that will be equal to mass into acceleration of the center of mass of this pull, and this is my equation 2. And now I'm willing to write the equation for rotation motion around the instantaneous center of rotation, that is passing instantaneous axis of rotation, that is the z-axis. So around z-axis I see the friction force and the normal or the gravity. None of them are producing any torque. About this z-axis, I guess only F is producing some kind of torque, but its moment arm is something like this. A perpendicular drawn from the instantaneous center of rotation to the line of action of the force F, and I named it D. So this is the only force producing a torque, and this will be producing torque in clockwise direction, as you can see here. So the torque is positive. So I'm going to write down the torque of this force F as simply as Fd, and that is going to be equal to moment of inertia multiplied by angular acceleration. And moment of inertia about this z-axis, I would simply write it I, and angular acceleration I am going to write in terms of omega as d omega by dt. So you can see here we got three equations. And what next we do? we can simply write the relation between d omega by dt, since it is not slipping, rolling without slipping. So I can simply write here A equals R alpha, or if you don't consider it writing, you want some explanation, I am also going to give you. Here you can see that this z-axis is the instantaneous center of rotation, and so it is at rest with respect to ground for the moment. At this moment, this must be at rest with respect to our what is called what is fancy name of it, lab inertial reference frame. So this would be at rest, and then that means from with respect to this point, its center of mass that is accelerating in this direction should be performing a circular motion of radius r. So from this point, its acceleration is simply two kinds of acceleration here. One is centripetal acceleration, that is also called normal acceleration, and another is tangential acceleration. If force is acting, you can see, so there must, the center of mass is accelerating, so there must be a tangential acceleration. So there are two kinds of acceleration with respect to the instantaneous center of rotation. One is omega square r, and next one is the tangential acceleration. You would love to write it dv by dt or d omega by dt multiplied by r. And center of mass, this instantaneous center of acceleration is itself accelerating with respect to ground in this direction, omega square r. This is at rest, but the things at rest can accelerate, and since this is not slipping, it will not have any acceleration like this. So its acceleration is simply in perpendicular to the horizontal surface, and you can see after adding them, you get the acceleration is equal to dv by dt, acceleration of the hoop as dv by dt, and this dv by dt can also be written as r d omega by dt. So it's simple, and it should not be, everybody knows it, there should not be an acceleration, should not be an explanation for this, but I gave one. Just don't mind, ignore it. So I'm going to write the kinematic equation, and I will be needing a geometric equation as well, and Steiner's theorem, that means parallel axis theorem. So since its moment of inertia about its axis, this axis of rotation I naught was given, and we need its moment of inertia about this z axis. So parallel axis theorem will be sufficient to write this equation. So I'm going to write three more equations, just three more equations, three more informations. The first of the thing is acceleration can be written as simply A equals r d omega by dt, and next is moment of inertia about the instantaneous center of rotation will be I naught plus its mass is also given mr square. So this will be an equation, and another geometric relationship we need to write here. How can we find d? So this is a right angle triangle, and this is the hypotenuse, and this angle is alpha, I guess, because this is angle between horizontal and this line, and this line is perpendicular to this line. D is perpendicular to the line of action of force F, and this line is perpendicular, so this angle is alpha, and so will be it. This angle will be also alpha, and here is a perpendicular. That means if we add both of the hypotenuse, then we will get r, and I know what the one thing, cos theta is written as base by hypotenuse. So I can write here hypotenuse equals base by cos theta. That means we can write here d by cos alpha, that is again d by cos alpha plus r by cos alpha is equal to r. This is our kinematic equation, and you can verify it with the photograph, with the diagram, with the pic, whatever you want to say, and like this. And after solving all this, after using all this, you can easily get the value of A. And I know you would like to have to find just three things: A, the friction force, and the normal force. Find all of them. Normal force is simple because it's n equals mg minus f sine alpha, so it's not going to bother you to find the value of normal, though finding the values of a and f is a good practice. And I know you will get a equals fr square by I naught, that is given in the problem, mr square cos alpha minus r by r. You're going to get this f. And why I was telling you to find the value of friction force, because to determine the coefficient of friction at which motion without slipping is possible, you needed to find out the value of coefficient of friction and the minimum coefficient of friction type of thing. And it is always possible when static friction at its max, that is, static friction is less than mu1 and its max, so its max value is of course f equals mu1. And you can find the minimum value of mu when f is max, so mu is simply m by n. So you needed to find out the value of a small f and n, and you will get your values of mu and mu minimum, basically mu minimum. And I can say I just found out the minimum value of mu that I would like to write mu is greater than equal to, because this is the minimum value of mu. You are going to get in this case f by mg minus f sine alpha I naught cos alpha plus m r small r capital R divided by I naught plus m r square. This is the minimum value of mu. And of course you can also find that the direction of acceleration of this pull is towards right, because in this case cos alpha minus r by r small r by capital R is greater than 0. And if it is, then the acceleration will be right. If it is not, then the acceleration will be left. And we can solve the thing accordingly, so you don't need to worry about anything. You got all your tools together. Thank you very much for watching.